Part 4 of this basic 7-part series is going to cover torque converters and their use in an automatic transmission. A torque converter is going to live between the engine and the transmission. It's the component that delivers torque from the engine to the transmission. It's filled with fluid, and all that torque transfer is done primarily through a fluid coupling. So there's no physical connection, at least until the torque converter clutch applies. More on that later, but during basic operation, there's no actual physical connection. It's all done through fluid. So that gets me to these 3 different purposes, main purposes of just a 3-element torque converter. One, which is a big one, the ability to come to a stop, or a stoplight, stop sign, without the engine stalling. On a manual transmission, I got to put my foot down on the clutch to disengage the engine from the transmission. On an automatic transmission, I don't have to do anything. Also, we're going to have this smooth transition of power when we go to accelerate. Since it's all done through fluid, when I go to accelerate, I usually get the engine to rev up and the vehicle to launch, and everything's smooth. There's no jerkiness involved. And that can also happen during the shifts. When I'm shifting from one gear to the next, that fluid coupling can kind of dampen things out. Lastly, we can multiply engine torque. We're going to get more into this later because we take this torque converter completely apart and I describe all the pieces and parts and how it functions. But basically this device right here, which is a stator, it allows for a redirection of energy in the torque converter, and that allows for a multiplication of torque. That's a benefit that we have using torque converters in an automatic transmission. But before we take this apart on the bench, we want to get familiar with a few different things, like some of the terminology. Here I've got an engine-driven component, we call it the impeller, and that's in green. Then we got the transmission-connected component, that's the turbine, and it's in pink. And that blue item here is the stator. That's the part that allows for redirection of fluid flow and gives us our torque multiplication. Down here I got a cutaway of the torque converter. This is a Honda 10-speed torque converter. It's got a lot going on in it. We'll actually see it. I take it apart on the bench and we look at the parts and pieces involved in it too. So of those 3 purposes I told you about a torque converter, where you got multiply engine torque, you got smooth acceleration, transitions between shifts, and the ability to let the engine to continue to run while I'm at a standstill or a stop. This is another benefit of a modern torque converter. Since the 80s, they've been putting lockup torque converter clutches in, and they're becoming more and more advanced. A lockup converter actually uses a friction disc to lock up so you get a 1-to-1 ratio. So what a lockup converter is going to do for you is it's going to allow the engine to directly drive the input shaft of the transmission through the clutch. So it kind of bypasses that fluid coupling that we have in there. Why would we want to do that? Because that fluid coupling actually generates a lot of heat, and that heat equates to energy loss. And the energy loss is going to be poor fuel economy. So by applying a lockup converter clutch where we allow the engine to directly drive the transmission component, we actually eliminate some of that loss. So modern transmissions that have maybe 5 speeds or more, 6 speeds or more, they're going to actively use this torque converter clutch. They're going to use it in many gears. It might come on as early as first gear, and they're going to do that to reduce the amount of energy that's lost during that fluid transfer phase that occurs in a torque converter. Let's take a look at how torque converters work with an automatic transmission. There are a variety of designs, and you'll see differences between them. This one, I've got a few different designs up here that I'll show you. This is not an in-depth lecture on torque converters. This is just a kind of a brief, how does this thing work and what's its purpose in the transmission. We'll look at more specifics on how they're controlled through hydraulics and so forth when we cover the transmissions in detail. But this is a typical torque converter that we have right here. This is actually off Honda 10-speed. When you pull a torque converter off the front of the transmission, you just basically have this big vessel that you're looking at right here. Now on all these, this one here is an Allison, and you can actually unbolt the halves on that. This is an Allison 3000, 4000 series transmission. But with all automotive and light-duty truck torque converters, there's a weld that exists, and you can't open this thing up unless you cut it on a lathe like I did here. And for that reason, most of the time when people are rebuilding transmissions, they put a new or remanufactured torque converter in. Torque converters are built and remanufactured by special facilities that do that. There are some transmission shops that have the equipment to do it themselves, but the vast majority of them order through their supplier remanufactured torque converters. And you know, these plants that remanufacture the torque converters, they cut them open, change the bearings, change the friction material that's in there, inspect everything, clean everything. A lot of times they replace this hub right here and weld a new one on and machine it. They balance it. So that whole process. Usually reman torque converters are, I don't know, 120 bucks or something like that. So it's a pretty typical expected expenditure when you're rebuilding a transmission, just to replace the torque converter, because that is the one area out of all the stuff that we rebuild that the average shop cannot go in and inspect themselves. So you don't want to take a chance of putting a bad part into a fresh rebuild. Also, if something fails in this unit or in the transmission, there's stuff that might get in here that you can't clean out. So that's another reason why you usually just replace them. But let's see how they operate, and that gives us an understanding of how what they do in an automatic transmission. So when you think about the purpose of a torque converter, in its name, it has torque converter in it. So it actually does multiply engine torque. That's a benefit that it has. During that process of multiplying engine torque, it creates a lot of heat, and that's a drawback that it has. Another big reason why automatic transmissions have torque converters is because this is the device that allows us, when we come to a stop, it prevents the engine from stalling. It's a disconnect, if you will. The torque, during acceleration and torque multiplication, the torque is transferred from the engine to the transmission through fluid. So when you come to a stop and your engine idles down and your wheels stop turning and the input to the transmission stops turning, well, there's no physical connection in the torque converter. It's all done through fluid. So it allows the engine to continue to rotate, and while the input to the transmission stays still. And then when you accelerate, the engine spins up faster and faster, and the momentum of fluid that it throws actually drives the transmission's input shaft. That's what we're going to look at, how it does that. So I'm going to show you the internals. Now, once again, this is the vessel that you get. Normally, it wouldn't be in two pieces. Usually, it would be one solid vessel because that is how the torque converter comes off. Let's take a close look at this torque converter. As I mentioned before, this was the Honda 10-speed. We're looking at the torque converter, the whole vessel, and I did mention that this is normally welded together. I cut the weld out so we can see the insides of this. Looking at this side first, you can see the center section is a hub. This actually fits this whole assembly. This hub allows me to center the torque converter into the transmission. So there's a bushing that this will ride next to, and that'll keep it all centered like it should be. You might notice these cutouts right here, these notches. A sprocket on the inside of the transmission is going to notch to this hub, and there's a chain that will allow the torque converter to drive an oil pump, and that's where we get the pressure in our transmission from. So whenever the engine's running, this whole thing's spinning, and we're spinning an oil pump through that chain and sprocket. So that is that's pretty much typical with all torque converters. When we look at some of these other torque converters, you'll see that they have some provision, like this one's got flats machined on it right there. And they have some provision to allow you to drive an oil pump. Sometimes there's a little mini shaft that fits in there. But either way, yeah, that's for the oil pump. And if we flip it over, there's a little weight, by the way. That's a weight for balancing that they put on there. And this part right here is the pilot that allows you to center the torque converter into the back of the engine. And the mounting pads for the flex plate, this allows the flex plate to drive the torque converter. And the flex plate's bolted to the crankshaft of the engine. So let's split this apart. Now realize that when the engine's running, this whole thing's spinning, right? Actually it'd be going the other way because the front of the engine is on this side, and this is the transmission side. So it'd be counterclockwise viewed from this side, but from the front of the engine, from underneath, it'd be clockwise. So this whole vessel's spinning. So when I pull this apart, the first thing you're going to see on the inside of this are these fins. Jeez, it's like a bell. Oh, it's this side. So when I open it up, the first thing that we see are these fins right here. Remember that this is normally welded to the cover assembly. So if the engine is rotating, these fins are spinning with it. Regardless if we're moving down the road or not, if the engine's spinning, this is spinning. And when you look at it, they've got this curvature to these little fins. And the purpose of that is when the engine is running, and it would be going in this direction. The purpose of that is it's going to take the fluid that's in here. Centrifugal force, when this rotates, is going to want that fluid to kind of fling around the outside, and the fluid that leaves this part is going to come over and contact the next part of our little assembly here, which is the turbine, this other set of kind of gold fins. I'll put this off to the side right now. This is called the stator. We'll talk about that here in a second. But yeah, so this is the turbine. And you're like, well, it doesn't really look that much different from the impeller. And really, the idea is the same. They've got these little fins, but instead of the engine rotating and throwing fluid out of the impeller like it's doing, the turbine is what receives the fluid. So this is the transmission side. The way I always remember it is turbine and transmission. Both start with T. So this is the transmission's input shaft right here. Kind of just show you that. Like this is on the inside of the transmission. This is the clutch assembly. Well, and there's also a set of splines, but this is the input to the transmission. So when the fluid comes from the impeller, when the engine's rotating, the fluid comes from the impeller, the turbine catches that fluid and it applies whatever force and torque from that fluid, it applies it to the input shaft. Now, okay, so if this is the transmission side, and it receives the fluid from the impeller, and then that fluid kind of comes back out. Well, what we have next is the stator, and that stator is going to be positioned right here in the middle. And the purpose of the stator is to redirect energy, the energy that has basically, so you think of the fluid energy that comes into the turbine, to a turbine blade. It absorbs all that force, so there's still momentum and there's still energy left coming out of this turbine. And if I didn't have anything like a stator to redirect the fluid in the same direction as the impeller that it's spinning, that fluid is going to actually push the impeller in the opposite direction. You're going to actually lose torque. So what they do is they put a stator assembly in there. It's upside down. Put a stator assembly in there. So the fluid that comes in to the turbine comes back out, and then it bounces off the stator blade and ricochets back in the same direction that the impeller is spinning. That allows us to multiply torque because we are basically recycling some of the energy. You've probably grown up with somebody or in your own house, you had an above ground swimming pool, right, in the back, maybe one of those 15-foot or 20-foot diameter swimming pools or like 4 foot deep. Well, what's the most fun thing that you can do in one of those swimming pools? You got it, create a whirlpool. So you get your buddies in there and you start marching around the outside of this circular pool. And if you imagine, you're getting this whirlpool, you're getting this current, getting all that water that's in that pool to start moving around. And the faster you go, the faster you go, the faster you go, the more current of fluid you've got moving around. We'll eventually get to the point where you can just, all that hard work paid off, and you could just kick your feet up and you're just sitting there coasting around and floating and having a great old time, drinking beer out of your koozie or whatever you do. Then, of course, there's always that one buddy that kind of falls in the middle, gets stuck upside down in the whirlpool. You got to pull him out by his ankles. But that's what's happening in a torque converter. I'm using this momentum of fluid. When that impeller is rotating, it's taking that fluid from my impeller, tossing it to my turbine. My turbine absorbs that fluid, and then whatever energy is left over gets redirected off the stator back into the same direction that the impeller is rotating. So I'm using the same force that I've created to drive the transmission to help the impeller spin. That's the purpose of the stator. It's fluid coming up from my impeller, gets tossed over to my turbine. My turbine absorbs it. Fluid that leaves the turbine bounces off a stator fin and goes right back into the same direction that the impeller is rotating. Torque multiplication. That all works great as long as the impeller is spinning faster than the turbine. Say that I'm at a stoplight and I go to accelerate. Well, my engine revs up and my vehicle just starts to move. So I might have an engine that's spinning 1500 RPM with an input to the transmission that's not really moving at all yet because I just started off from the stoplight. So at that point, my impeller is spinning a lot faster than my turbine. And during that mode, there's a lot of this fluid that's coming from my impeller to the turbine, to the bouncing off the stator, redirecting it towards the impeller, impeller, turbine, stator, impeller, turbine, and you're doing these little loop-de-loop, these little slinkies. That's called vortex flow. Vortex is this little swirl that's happening. There's a lot of heat created during that, and there's also a lot of torque multiplication because I'm recycling a lot of that energy. Now let's take it to the other extreme. Now I'm going down the road after I've just accelerated from the stoplight. I got up to 50, 60 miles an hour. Now I'm letting off on the throttle. There's not that much speed difference now between the turbine and the impeller. The engine and the transmission input shaft speed are going pretty close to the same speed. So if my turbine is spinning fast along with the impeller, the fluid that's left over and that comes out of the kind of the bottom here or towards the middle of the turbine blade, it doesn't want to hit this flat spot right there. It ends up hitting the back of these stator blades. And if I don't let this freewheel, notice how it's got a one-way clutch in there? If I don't let that freewheel, it'll actually redirect in the opposite direction of the impeller rotation, and that would slow the engine down. That's what we call rotary flow or coupling phase. So under acceleration, it hits the front of the stator blade, ricochets off in the same direction as impeller rotation, but once I get up to coupling phase or cruising speed, and the turbine and the impeller are going pretty close to the same speed, the fluid wants to hit the back of the stator blade, and it's allowed to push the stator out of the way. The stator splines to this second set of splines right here. These splines, this is the input shaft spline. You can see I can move it. This set of splines right here are the stator splines. They're bolted to the transmission case, so this part doesn't ever move. You can actually see the little raised sections on the casting there. That's where the bolts are coming in from the other side. So the stator splines, the stator will spline to that shaft that's permanent and that's mounted to the front of this transmission. So it'll allow it to freewheel in one direction and hold in the other. So that's how we're able to hold a stator. Looking at it in this direction, this is the turbine side of the stator. So when fluid's coming during torque multiplication, when the impeller is spinning a lot faster than the turbine, fluid's wanting to hit it here on this part of the blade, and then we're going to get a redirect of fluid going right in the same direction as impeller rotation. Now, as you get closer to cruising speed and the turbine starts catching up to the speed of the impeller, the fluid slowly starts creeping around. It doesn't want to hit this side of the blade anymore. It wants to hit this side of the blade. And if I don't do anything, if I just hold the stator all the time, it'll actually ricochet back in the opposite direction of impeller rotation, and that would be bad. It'd feel like somebody's hitting the brakes when you let off the throttle. So what they do is they have that one-way clutch that's in here. So when fluid wants to hit the back of it, it's allowed to push the stator out of the way. So it locks in this direction because we need to redirect the fluid flow for torque multiplication, and it freewheels in this direction because when fluid hits this side, we don't want it to redirect because we'd be going in the opposite direction of impeller rotation, and that would be bad. Now we actually have a fourth part that we haven't talked about yet, because back in the old days, 50s, 60s, 70s, that's all they had for torque converters. They had an impeller that was engine driven, a turbine connected to the transmission, and a stator that allowed for torque multiplication. As we know, fuel economy and emissions make up a big part, so they added an additional component to a torque converter, and that's the torque converter clutch. And this is where there's a lot of different designs. This is called a captive clutch, and it's not unlike the multiple disc clutches that we just talked about previously. When you look at it, it's just, we just got steels, friction steel. There's 2 friction discs in this one. And there's a thicker backing plate, a little thicker, so that way it can absorb the force of the hydraulic piston. This piece is a little cushion spring, so that way when the clutch applies, it doesn't just bang on that clutch assembly. When the piston applies, it will deflect this and allow it to kind of smoothly apply. So this is the piston. It's a steel piston, large surface area. Well, a large surface area with a little bit of pressure behind this thing will actually get quite a bit of force on this piston. And I guess I could show you to seal that off, they have O-rings in there. The O-ring for the middle is in this hub section, and the outer O-ring is built into the piston. When this piston comes up, it's going to compress this clutch pack. And this clutch pack is splined to the turbine. Right there. So you can imagine these clutches, these steel plates are lugged to the cover of the torque converter, and these friction discs are splined to the turbine. And they got little cushion springs and so forth in there, almost like a clutch on a manual transmission. What'll happen is when the time comes, they can apply this piston and lock the converter housing to the turbine. And if you remember, the turbine is splined to the transmission's input shaft. So once we're up to speed, or we have to get going very fast on these late model units, they apply these torque converters really quick and basically let the engine drive the input shaft of the transmission through this clutch assembly. So here you can see the fluid to apply this clutch is actually going to come in right through the middle, and that clutch will come up and apply. The way it gets in there is through the input shaft. So with this in there, and there's two holes, so I got to cover my finger over one. You can see that piston go up and down. Applied, released. Applied, released. Applied, released. Okay, so that is how this clutch works. And as I mentioned, when I apply this clutch, I just lock the turbine. When that clutch is applied, this turbine won't spin. I don't have that many hands available, so I went ahead and put a C-clamp on this. But you can see I can spin this assembly. When I apply the clutch, it locks. Spin, lock. Spin, lock. So that's the idea of this lockup converter, is that when I apply this clutch that's in here, when I apply this clutch assembly, it's going to lock itself to this turbine. This turbine locked to the cover, it's going to drive the input shaft. So I'm going to have an engine that's kind of bypassing the torque converter and driving the input shaft. This lockup converter thing, that's a big deal on modern vehicles. We've got all these speeds now in these transmissions, like a 10-speed. They'll bring a lockup converter on in first gear, second gear. I mean, they won't even just bring it on completely. Sometimes they'll bring it on just a little bit and let it slip. So a lot of strategy has gone into how these torque converter clutches work, because what they're trying to do is make these vehicles so fuel efficient, and we can't lose a lot of energy through creating heat in a torque converter. So as soon as they can apply this clutch, the less energy loss to a torque converter and the more fuel economy. All right, so this is that Honda, and we hopefully understand the major parts. The turbine, remember turbine and T. Turbines are connected to the transmission. Stator, purpose of the stator is to allow for a redirection of fluid flow during torque multiplication, and that allows you to get torque multiplication. And then the cover has the impeller built into it. And then on the outside, we've got our hub that allows us to center it to the transmission and also drive an oil pump. And on the other side, we've got a pilot that allows you to center it to the crankshaft and be driven by the engine's flex plate. And this whole assembly is welded together. Now let me just show you a couple little differences. This one here is from the Ford 6F50. functionally, if you look at it, it's like, oh, it don't look that much different to me. I got a pilot, got 3 mounting pads. I got flats on this instead of a notches, because this, just the way it drives the pump is different. It still drives the sprocket, but when you look at the inside, the impeller is still got an impeller, a lot of braze. By the way, this gold color is brazing. They put like a powder in there and they furnace braze it. They put it in an oven, and that's like soldering all these parts together. Not all torque converters do that. Sometimes they just crimp them over, and this is kind of a nicer option. Here's their stator. This is their turbine. So this turbine's a little different. It's got these little tabs welded to it, and those tabs grab onto this disc. So instead of using multiple disc clutch assembly like we did on the Honda, and you know, this is actually definitely a more common setup, is using just one solid disc here. And they're going to operate the torque converter clutch a little differently in this. When this vehicle is operated with the lockup converter off, what they do is they pump fluid in through the middle of this piston, through the input shaft, and the fluid enters the torque converter between this cover and this hydraulic piston, where the friction material is and all that. That's where they enter the fluid in. So by pumping fluid in through this way, it causes this piston to move away from the cover. They do that on purpose. That prevents this clutch from coming on. And then when they want this clutch to actually apply, they'll reverse that. They'll bring the fluid in on this side, and kind of it'll try to find its way back, in a sense, at least for a little bit, through the middle. And by doing that, this piston is going to get the kind of more of a pressure on this side of it, and it's going to drift towards the cover. And then when this piston comes into contact with the cover, it creates a natural seal, and then boom, you get all that converter pressure working across this whole piston, and you get a lot of force. Now this piston is lugged to, that's what those tabs are doing. This piston is lugged to this turbine. So when I lock this piston to the cover, I'm driving the turbine, and the turbine is connected to the transmission's input shaft. So this is a 6F50 Ford transmission, and so this is the input for it. Oh, everything heavy. So you can imagine when I apply this lockup converter, and it grabs onto the torque converter cover, which is bolted to the engine and so forth, it's going to deliver torque directly into the transmission, bypassing, in a sense, the action of the torque converter, and that allows for what we call the torque converter lockup, right? So this is a little different than the Honda. You could see the single friction surface that they've got there, and it's a big plate that ends up contacting the housing. This is actually a more common way for a lockup converter. Things are moving to the multiple disc clutch type, but this is probably still the most common setup. So turbine with the big converter piston in there. We still got our stator that's going to redirect fluid. So the operation of the torque converter doesn't change. The only thing that's different is that piston. All right, that's that one. And then over here, this guy right here. This is off the 10-speed Ford, 10-speed GM. They both use this design. And it's a lot different than these others. It still has a stator, impeller, turbine. We still have a hub that drives a pump, and all that stuff's the same. Still mounting pads and pilot for the back of the crankshaft. But what makes this different is when we pull it apart, you'll see a machined surface on the transmission side of the cover. And built into the turbine is a flange that has the torque converter clutch material on it. So that's a little bit different. This surface, which is on an angle, matches with this surface here. So this is going to probably create a little bit of a snafu for the remanufacturing facility. They're going to have to figure out ways to machine the surface smooth and bond, because they use heat and pressure and glue to bond these friction materials on it. Well, now whatever they have is going to have to do it on an angle, so that's going to be a little different. Stator's still a stator, nothing fancy going on there. The big change is this flange right here on an angle, and it's connected to the turbine directly. It's not a separate piston, and it has actually, they move the whole turbine assembly towards the transmission to apply onto that surface area to get this converter to lock up. And that's something that's different. On this side of it, you can see they've got a ton of these pins and rivets, and in these springs to absorb to dampen vibrations. It'll be interesting to see how the remanufacturing industry addresses this. Let's talk about some of the terms and tests and characteristics that surround torque converters. You might have heard the term stall speed. That gets thrown around a lot when we talk about torque converters. The stall speed actually does have a value for diagnostics, a pretty good value. And let me describe what a stall speed is first, because to hear the name stall speed, you might think that's when the engine stalls. No, it's actually not, doesn't relate to that at all. I think, but I'm not 100% certain, that it comes from maybe the aviation side of things. Matter of fact, a lot of these parts, when we start thinking the names, impeller, stator, turbine, those kind of have connections to the aviation industry. But in an airplane or a jet or something like that, the stall speed is like if you were to fly that thing towards space and it kept climbing and climbing and climbing, you're wide open. You're just blasting away, going as fast as you can. Well, eventually, you're not going to be able to climb any higher. You're going to get to a certain altitude and you're going to stall. The engine's not going to stall. You're still going to have 100% output, but you're just not going to get any more energy. You're not going to get any more movement out of that plane. So the same thing is similar with a torque converter. The stall speed is if I were to keep my wheels from moving, brake, by applying the brakes or whatever. So my transmission and my turbine, because remember what's connected to the input shaft of this, I'll use this torque converter since I got this big old input shaft here. Remember what's connected to the input of the torque converter is the turbine. The turbine drives this input shaft, and the fluid coming from my impeller pushes up against the turbine, and that rotation tries to drive my input shaft. Well, during a stall test, I'm spinning my impeller or my engine side as fast as it'll go without getting any movement out of my turbine. So that means this engine is going, let's say 2,000 RPM, but my turbine's not going any faster. So if you thought about what's happening to the fluid during that situation, I've got fluid coming from my impeller to the turbine, bouncing off the stator, back in the same direction as my impeller, back to the turbine, back bounces off the stator. So it's impeller, turbine, stator, impeller, turbine, stator, impeller, turbine, stator. We just get this loop-de-loop-de-loop-de-loop. It's sitting there swirling like crazy, right? Getting as much torque multiplication as I can. I'm redirecting with force as much of that fluid from the turbine off the stator in the same direction as the impeller. So I'm actually pushing on that volume of fluid that it's moving. I'm helping it out as much as I can with that redirected energy. But there's a point where my engine is only so strong, it can only throw so much fluid, and it's only going to get so much help. So the engine speed is going to climb up to a point, maybe it's 1,800, maybe it's 2,000, maybe it's 2,500 RPM, and that's as high as it'll go. I can't get it to go any faster. That would be the stall speed. So if you see like a spec in a book that says stall speed should be around 1,800 to 1,900 RPM. So if you were to test that, you would put it in drive, you would be in a safe spot, you'd apply the brakes as hard, a lot of force, parking brake, the whole works, and go wide open throttle. Not half throttle, not quarter throttle, you go wide open throttle. And what you're doing is you're applying as much force from the engine to this torque converter and having this spin as fast as it can go, the impeller spin as fast as it can go, with the transmission's input shaft spinning 0 RPM. So it'd be impeller, turbine, stator. It's going to climb hopefully to that spec. It's going to be in that range. If it doesn't get to that range, if it can't climb that high, there's a couple things that could be wrong. Now, I sometimes challenge the students into thinking about this. I'm like, okay, if I did a stall test and let's say, make it easy, the spec is supposed to be 2,000 RPM, and let's say they perform the stall test and you got 2,500 RPM out of it. What could be wrong? Well, in most cases, what would be wrong would be as a clutch and the transmission is slipping, not in the torque converter, but in the transmission, and you're actually getting input shaft rotation. If you do a stall test and let's say 2,000 RPM is still the spec, and you're only able to get 1,500 RPM or 1,200 RPM, what could be wrong? Maybe even less than that. Okay, for one, let's think about this stator. What's the purpose of the stator? It allows that fluid from the turbine, the leftover energy, to bounce off the stator blade in the same direction as impeller rotation. Well, imagine if this one-way clutch in there wasn't holding and it was allowing it to move. That fluid that would be coming in there wouldn't be bouncing off of the stator blade and redirecting in the same direction as impeller rotation. The fluid that's left over would actually interfere with the impeller rotation. So that, if a one-way roller clutch was not holding on your stator, that could cause a low stall speed. Also, another one is your engine performance. Well, I mean, the source of the RPM and the power is coming from my engine. So if my engine is in need of a tune-up, if I've got a clogged fuel filter and I'm not getting as much fuel, clogged air filter, a restricted exhaust, timing that's off, cam timing or ignition timing, any of those things could lower the output of my engine. And if I lower the output of my engine, then I can't spin these parts up as fast. And that's going to lower my stall speed. Think of the example I gave you with that above ground swimming pool. That might clear up a little bit of confusion if you're still struggling with the topic a little bit. So if I go back to my analogy with the above ground swimming pool, and I had, let's say, 4 people or 5 people marching around the outside of that pool, getting momentum and getting that current flowing and circular and all that stuff. Now I'm going to give you a couple different options. Same swimming pool, but we've got 4 middle schoolers in there that are 10 years old, 11 years old, haven't hit puberty yet, they're not strong. How much of a current and how much momentum of fluid do you think they're going to be able to create? Now let's say we take this Saluki defensive line and you got 4 of their strongest guys in there and they're marching around this thing. They'd probably be marching around that little above ground pool so fast that water would be pouring out the outsides. So that's happening in my torque converter, but instead of the middle schoolers and the football players, I've got an engine with a certain amount of torque, certain amount of horsepower. So a stronger engine will be able to drive these parts faster and the stall speed will be higher. A weaker engine won't be able to achieve that. We're just not going to get the strength and the momentum and the force of the fluid in here, so the stall speed would be lower. A lot of people want to think that something in the transmission or the torque converter is slipping if you've got a low stall speed. And the only thing that could be slipping is that one-way clutch, because then you're not getting the redirection of that recycled energy from the turbine. So for the most cases, if you've got a low stall speed, you're dealing with a one-way clutch that's slipping, or you're dealing with an engine issue. If you have a high stall speed, you're dealing with something in the transmission that's slipping, or you got a stronger engine maybe. Maybe you did a modification to your engine, but yet you didn't change anything in the transmission. Your stall speed might be higher now because of that. So that is one thing that people will do with the automatic transmissions and diagnostics as far as the torque converter is concerned, is they'll perform a stall test. And if the stall test isn't within spec, then they can kind of get a direction to look. Look at this big old hoss of a torque converter. This is off of an Allison 3000, 4000 series. I got a couple of these donated. And this, here's our impeller, big old mama. And here's the big old stator in there. You can probably see why we got this. The bearing kind of destroyed itself on there. Surprisingly, it didn't really damage the impeller side at all. And here's the turbine. I'm going to pull it out. Remember earlier I was saying that sometimes they don't braze these, and you can see right here on this turbine, they just crimp these over, big chunks of steel, so maybe the size of it kind of allows them to get away with that. On the impeller side, it is brazed to it. And then our lockup clutch is kind of the separate pressure plate assembly that we have here. So there's our friction surface. So that whatever life this thing had didn't affect the torque converter, it didn't affect the converter clutch at all. And then if you were to rebuild this thing, that says piston plate side. And it doesn't say anything special on this side, but this is the piston in here. So it's telling you that when you go to put it together, make sure you have it in that direction, not in that direction. I don't even know. There's no way you can put it in that way because the hub will keep it away from the cover. So, but you know, like they always say, somebody will try it, right? So I'm not going to try to pull this piston out, but if I turn this over and slapped it on the table, this piston would come out, and I can change the seals on it. So here we have Allison's 3000, 4000 series, something you might find in like a dump truck or something like that. And it's kind of nice because they give you the capability to rebuild this thing. So even in a heavy-duty torque converter, that'd go in something like a garbage truck or like a big old dump truck or something like that, the major components are still there. We still have a turbine, still have a converter clutch, still have a stator to get torque multiplication, and we still have an impeller. Now this thing's nice because you get to take it apart, inspect it, and buy parts for it and rebuild it. And you don't have to send it off to a shop. You can go through and do all that testing and verification and measurement yourself to see if it's good or bad.